In this midterm, sample midterm, we have 6 problems. Question 1 has 8 parts, just complete. For example, the first one, give one characteristic of thermal energy reservoir. Just you can say this is one characteristic, or the main characteristic. It has infinite capacity. He said, what is the Kelvin Planck? Kelvin Planck, as you remember, if you cycle like this, he said, it's impossible to have this. If you have 8 engine, you cannot have single reservoir. Say it in your words, anything. For example, it's impossible to have a design, to have an engine that has works operating a cycle, receives heat from single reservoir and produce network. It's impossible. You cannot have this design. Violates second law of thermodynamics. Name 2 ways to increase the COP. Sometimes we use COP, refrigerator, let's say refrigerator, or beta, just a symbol like eta. Eta for heat engine, beta for refrigerator and heat pump. So beta refrigerator was, we derived before, T high over T low minus 1. This is, we derived it in the beginning of the review. What are the 2 ways to enhance Carnot? This is Carnot. It was Q high over Q low minus 1 for the real heat engine or heat refrigerator. Now it's Carnot refrigerator. So simple way, increase T high, decrease T low. Let's say, mention here, the first one, increase T high. The higher the T high, the better refrigerator is. Or decrease T low. The lower the T low is, the better your efficiency. If T low is 0, which is impossible, you have 100% efficiency. If you have T high infinity, which is also impossible. So increase T high or decrease T low to enhance the COP. So increasing T high or decreasing T low is the way to increase or enhance the COP of a Carnot refrigerator. For the first one, for a particular closed system, like there is no mass flow rate and just Q minus W equal delta U. This is the first law of thermodynamics for closed system. Operating on a cycle. It has a cycle. Started from here, ended here. That's cool. If it's a cycle, of course delta U equal to 0 because it's a cycle. There is no change in internal energy, total internal energy. The net work was 0. There was no work. So we have Q minus 0 equals 0. So Q equals 0. What is this, guys? Is adiabatic. What you need to do is come here and say adiabatic. That's it. Q equal to 0. Name, problem number 5. Name 3 ways to transfer heat in or out a system. Heat. There are 3 ways we discussed in the lecture about how to transfer heat from to the system. Convection, conduction, radiation. If you know it, 0 time, 1 minute to write it. If you don't know it, you need to go and study, and it's kind of a waste of time. For the part number 6, true or false. Enthalpy can be neither created nor destroyed. Nope, it's an energy. Enthalpy is internal energy plus flow work, is not the whole energy. So this is false. Number 6 is false. Just mention false. Does a cycle for which the net heat integration of Q is called net heat, positive, of a cycle? This means cycle. Violate the Clausius? Nope. No. Clausius statement means something else. Clausius statement is this. This is Clausius over T. This is a property, but this is not. This means we have net heat in the system. Can be heat addition, heat rejection, or no heat, like adiabatic, like problem number 4. So this one, nope. This is, no, does not. In the space below, it was space below, draw an engine, heat engine. You have inputs, you have output, Q low, W net out. You have Q high, And it's also T low, T high. T high, and this is T low. That's it. This is the heat engine, HE. Define the thermal efficiency. Remember, this problem can be totally different. Can be, I can ask you refrigerator. I can ask you for heat pump. So remember, focus what you are drawing. So for heat engine, eta thermal, for real and ideal. For real, it's 1 minus Q low over Q high. W net out over Q high. Eta thermal, ideal, which is Carnot, 1 minus T low over T high. This is only if it's Carnot. This is always correct. This is always correct. Now we finished the first question. This question is supposed to be 10 minutes in the exam. This question is supposed to be 10 minutes in the exam. The second question, it's a 0.3 meter cube rigid tank is filled with saturated liquid, X equals 0. So we have state 1, X1 equals 0. Temperature was 200. Temperature 1 was 200. Actually, this state is completely defined. They have two independent intrinsic properties. A valve at the bottom of the tank is open. There was a valve here. This one, it's open. And the liquid withdrawn from the tank, heat is transferred to the water. We add heat. This Q high, add to the system. This Q high, can you see it? This one here, add to the system. Q high. Such that the temperature in the tank remain constant. Oh, good. So T2 equal T1 equal 200 Celsius. So temperature remain constant in this process. Determine the amount of heat must be transferred. How much watt or joule I added to the system. Joule here, because it's unsteady open system. Determine the amount of heat. 1/3 of the mass escape. So 1/3. So the mass here was M1. So initially we have M1. V1. Finally, we have 2 over 3 M1. We have V1. So the same volume, but with lower mass and some mass escape. So we have exit. Let's say exit here. It was T was the same. T exit was the same. 200 Celsius. And the mass exit was 1/3 M1. So this and this and this are the continuity. M1, there is no late, but M1, 2/3 remain, 1/3 escape, withdrawn from the tank by opening this valve. He wants the amount of heat, Q, of this problem. He wants the heat of this problem. Let's start with the first law of thermodynamics for open system unsteady. So Q minus W plus Mn times something minus M out, which is exit times something, equal M2 times something minus M1 times something. There is no mass in, there is no work. We have just H exit, there is no kinetic energy. We have just U2, we have just U1. We neglect kinetic and potential energies. So this equation would be Q. What I want is M exit, H exit, the enthalpy of the going out mass plus M2 U2 minus M1 U1. So M exit is 1/3 the M1. M2 is 2/3 M1, and this is just M1. So if I have M1, I have all the masses. H exit is state exit. Actually, I have it. It's 200 and remains liquid. So H exit is still 0. So I can get H exit. So this is saturated liquid. 1, the same. I can get saturated liquid. State 1 is totally defined. The problem with 2. 2, we only have T2 equal 200. What should I do? So here, we need to get, before we do the go to steam table, we need here mass 1. Mass 1 is simple, by the way. So from state 1, you can get V1. You can get H1, which is actual H exit. You can get U1. Mass is V over V. volume over a specific volume, you can get how much mass, because this volume per unit mass. This is the volume, which is given 0.3 meter cube. You can get M1. And this volume 1 is equal here, equal volume 1. So V2 is the V1. And if you get M1, once you get M1, you get M2, you get M exit. Once you get M1, you get M2, you get M exit. All the masses are now given. And also you get V2, which is volume 2, which is constant, because this is rigid tank, over mass 2, which is 2/3 mass 1, the remaining mass in the tank. That's so simple. Get V2, and you have T2, you can get everything, which was probably saturated mixture. Saturated mixture. Let's see the table. So remember, state 1, saturated liquid, mixture, liquid, x equals 0. So let's look at these in the table. This is the table here. This is state 1. You have temperature. You have the temperature T1. You have the X1. You can get the temperature 200, table A4. You can get, because X equals 0, only look at F, subscription F, which is liquid. So you can get the VF, the first one. You can get the UF, HF, SF if you want. So we just need this VF, which is V1. We need UF, which is U1. We need HF, which is H exit. The state 1 similar to a state exit. From V1, we can get M1. M1 again is V1 over V1. Volume 0.3 meter cube over V1, which is 0.0011. 0.01157, which is 259.2.3 kilogram. 1/3 escape, which is 86 kilogram. 2/3 remain, which is 172.86 kilograms. We have now everything U1, H1. That's we have. You have U1 and you have H1 or H exit. Let's go to the state 2. State 2, very similar. State 2, we have V2. Now, V2, specific volume, is volume 2, which is the same 0.3, divided by mass 2, which you already got it. Mass 2 was 172.8, which is 0.0173. Guys, 0.0001, this is the most important number in your life. 73 meter cube per kilogram, almost 1 liter. However, the mass is huge, 86. But you still took per unit kilogram, because the tables are written by terms of per kilogram, intensive properties, specific properties. So we have V2. V2 is in between VF and VG, as you can see here, between VF and VG, like it's greater than VF, lower than VG. You can get X2, just simply V2 minus VF over VG minus VF. You can get X, which is just 0.00 or 0046, almost 5% or less mass of vapor. The rest is liquid. So you can get H2, which is what I want. H2 is HF plus HX2 HFG, the same temperature, which is 200. The process was 200. That's why I go to the row 200 and got H2. So the Q now is M exit, H exit, which is H1, plus M2 U2 minus M1 U1. So the initial energy, the final energy, plus the escaped energy. You can get Q, everything you have. Once you get the mass all the states you have. It's 1.539 megajoule. 1,539 kilojoule, or 1.539 mega. Problem number 3. Refrigerant or fluid, table 12, 13, 14, or 11, 12, 13. Refrigerant 134A or fluid, this are fluid going through a pipe, throttling valve with pressure decreased from 700 kilopascal to 160 kilopascal, a little bit more than 1 atmosphere. Saturated liquid, initially X was 0, so we have inlet and we have exit. Inlet X was 0 because saturated liquid, not vapor. So X pressure was very high, 700, saturated liquid. So we have everything at 1, P1 and X1. Determine the temperature drop, delta T, T2 minus T1. If I have two independent intensity property at 1, I got it. Two independent intensity property at 2, I got it. So I can get the delta T. And the final specific volume, V2. At 2, I only have now P2, which is 160 kilopascal. Before going to the tables, let's see what is missing. Let's write the first law of thermodynamics. Q minus W. We have only this steady, so the right hand side is 0, plus M dot, let's say this, everything is dot. H in minus M dot H out. Or 1 and 2. There is no heat, there is no work. Divide by mass, so H1 equal H2. That's it. This is total enthalpy remain the same. Enthalpy, internal energy, and flow work. Internal energy may increase, decrease, pressure may increase, decrease, but the total enthalpy remains the same. If there is no heat, there is no friction, there is no work. Of course, there is no work. This is just a valve. M dot delta H equals 0 because it's steady state. So this is a reduced form of first law of thermodynamics. So you have everything in set 1. You can get everything, including H1. Give it to H2. Once you have H2 and P2, you have everything in state 2. So finally, H1 equal H2. This is what we concluded here. H1 equal H2. State 1, we need H1, of course, needed for this. We need T1. That's it. We don't want anything else. For pressure 2, we have H2 equal H1. Now, it depends. If H1, H2 is in between HF and HG, saturated mixture. Lower than HF, compressed liquid. Greater than HG, superheated vapor. For this R134A, do not go to the other table. 11, 12, 13. Tables. Okay, let's check the first table, first state. First state, X equals 0 and pressure 700. So open A12. Actually, A11 was temperature. A12 is pressure input. So go to the row of 700 kilopascal. The very bottom, this row, this 700 kilopascal. As you can see, the first one is pressure, temperature, saturation. Then V, F, Vg, UF, UFG, and UG. Then H, then finally entropies. So 1, 2, 1, 1. Then 2, 2. Then 3 internal energy, 3 enthalpy, 3 entropies. We need H1, we need T1. That's simple because everything is X equals 0. It means saturated, F, subscription F. Just take these values. The first one is VF, is V1, if you want it. We don't want it. U, U1, we don't want it. H1, we want it. We want T, so we take the T, we want it. T is before VF, this T, before this guy here. And H1, which is this guy here. So get H1, and H1 exactly H2, which was 92.22 kilojoule per kilogram. And T1 was 26.69, just Celsius, of course. So we have two things about state 2. That's awesome. Go to find out state 2. This is state 2. Now go to the row pressure 160. The pressure is a little bit lower than the other one. Check first. Table it will check this. You will find that yours is in between. So this enthalpy between Vf and Vg. In these three parts, before the end, before entropy, we have enthalpy. These three values, Vg, Vf, Vg, and Vfg, you are between Vf and Vg. It means you are saturated mixture. You can get the quality. So quality is H2, quality 2, minus HF over HFG, which is here, the quality was 0.290. Oh, so in this expansion through the valve, reduction in pressure, some of the liquid, it was completely liquid. Some of the liquid became vapor. It means with higher energy. It means we have quality, we have more masses in vapor. 0.2, 30% almost became vapor from this equation. Now we can get everything about 2. We can get, for example, T2, which is the same temperature, 160 saturated temperature, which is minus 42.29 Celsius. We can get V2 from V2, again V2, the same as before, Vf plus X Vfg. So we take these V's, the volumes, Vf and Vg. So Vf plus X, Vg minus Vf. So we can get V2, which is 0.03 meter cube per kilogram. So the good news is delta T, we don't need to convert it to Kelvin. But if you do that, I would prefer to just stick to the rule. Delta T Celsius equal delta T Kelvin. But temperature Celsius does not equal temperature Kelvin. The difference is 273.15 Kelvin. So you need to add to this some term if you want to use it. For example, it was not here, in ideal gas law, in entropy calculation. So do not blindly use it. Unless you understand this is delta T, doesn't matter. Add 273, subtract 273 is the same as delta T Celsius or delta T Kelvin. They are the same in units. So remember, if you know the steps, it will be like less than 10 minutes. But if you don't know, it's much more than that. And I would prefer to solve a lot the homework and problem lectures and problem quizzes. Problem number 4 was a cylinder with a linear spring. Linear spring means when you plot the PV diagram, let's say this is P1, this is P2, V1, P1, V2, P2, it's a linear. So this is a VP diagram. So this is called linear spring loaded piston cylinder, contains a carbon dioxide. So we have here trapped carbon dioxide in the yellow. Gas. I can compress it, expand it easily. That's a gas. We can use here ideal gas law. At 2 megapascal. So at state 1, so we have here state 1. We have P1, 2 megapascal. Initially, it was, the volume was 50 liter. The volume 1 was 50 liters. 10 minus 3 meter cube. Devices of aluminium. So this one bar is aluminium. The bar here above the carbon dioxide bar, aluminium, has mass 40 grams. So this aluminium bar, if you want to draw it, is a spring. Oops. This aluminium bar, this is a spring. This aluminium bar has mass of 4 kilograms. Everything was 200. So temperature here 1 was 200 Celsius. Temperature here was 200 Celsius for aluminium or for the carbon dioxide. Ideal gas. Do not forget about your steam tables now. The heat transferred to the system, from the system to the surrounding, and the surrounding was 25. So it cools down to 25. So it means T2, 25 Celsius. The pressure was P2, 1.5. I have everything state 2. This is T2, became 25. Dropped from 200 Celsius to 25 Celsius for aluminium. Here drops from 200 to 25 as well. Find the total entropy generation, delta S generation. We have three things here. We have delta S carbon dioxide between 1 and 2. We have delta S aluminium between 1 and 2 for aluminium. We have delta S surrounding. The surrounding has constant temperature, so this is the easiest one. Just in terms of equation, Q over T, which is 25 Celsius. Add, this is 25 plus 273. We need to get the Q. To delta S CO2, simple. Delta S for ideal gas, mCV ln T2 over T1 plus M or ln V2 over V1. So we need to get the M for the carbon dioxide. We have T2. We can get V2 and V1 because we have everything in 1, everything in 2. So from this volume, we can get mass. Simply, you can say PV equal MRT. We have pressure 1, volume 1, R from table A2A, or A2, A1. Temperature is given in, it must be again in Kelvin, 200 plus 273.15 to be in Kelvin. So you can get the mass. The mass was in kilogram. Point 671 kilogram of carbon dioxide. That's easy. You have T2, you have T1. V2 and V1, just simply P2 over P1, V2 over V1 equal MR T2 over MR T1. So you have P2, P1, T2, T1. You can get V2 over V1 and put it here. Because ideal gas law, valid for 2, valid for 1, ratio, get V2 over V1. You have T2, you have T1 in Kelvin. So this should be Kelvin, should be Kelvin. You can get the ln part. CV and R are from table A to A. So if you go to table A, like this, for carbon dioxide, you can get K, CP, CV for carbon dioxide. K is specific heat ratio, CB is heat capacity at constant pressure, CV heat capacity at constant volume, R is the difference, CP minus CV, which is gas constant. We use it in here, for example. Okay, guys, so the first one is done. This is delta S for carbon dioxide. Delta S aluminium is so simple. Delta S, this is incompressible or solid. Just M, C, ln T2 over T1. We have T2, we have T1 in Kelvin. We have heat capacity, we have the mass, 4 kilograms. Heat capacity also is given. If you read the problem carefully, he gave the aluminium heat capacity 930. 930. The very end of the line, the problem. Maybe I did not specify, but it's given in the problem, the heat capacity. Maybe under this. If you go to the lecture, it's given in the exam, 930 joule per kilogram Kelvin. So this is simple, so simple. The last one is a little bit harder. However, the equation is so simple, but a little bit harder. How? Q. Now we have two heat rejection here. Heat from the carbon dioxide and aluminium. So this Q is two Q's, Q CO2 plus Q aluminium. Q aluminium is simple. Q aluminium is so simple. It's MC delta T. Mass of aluminium 4 kilograms, C aluminium 930, joule per kilogram Kelvin, delta T 200 minus 25. Delta T is okay. The Q CO2, according to the first law of thermodynamics, is equal W plus delta U. Q minus W equal delta U. This is gas. So we can say just W plus CV MCV delta T. So we have CV carbon dioxide, delta T carbon dioxide. We have the mass. We got it already from the ideal gas law. We need the work. The work is this. This is the kind of the hardest part. This is a spring, go from this pressure to this pressure. and expand like this because we reject heat. So the area here can be trapezoidal area. This plus this over 2 times this. So it's P1 plus P2 times V2 minus V1. Actually, if you want to get the work, V big over 2. You have V2, you have V1. Actually, V2 you have. V2 is here. PV equal MRT. The mass doesn't change. So P1, P2, V2. So the mass is the same from M1. So you can get V2. You have V1, you have P1, you have P2. You can get. Or triangle area plus rectangle. This, which is P2, times this, plus half of this times this. The same. This is the work. Once you get the work, joule, internal energy, CV delta T, in joule, MCV, mass, which is M1, the same. This is in a closed system. It's closed. There is no carbon dioxide escape. You can get the Q. Once you get the total Qs, which is mostly negative, you put it in this equation, but it's positive for the surrounding. So this Q, yes, it's negative because it's keeping from the carbon dioxide or aluminum. But with respect to surrounding, it's input to surrounding. It means it's positive for the surrounding. That's why we put a positive here. That's why this entropy would be bigger. This is negative. This is negative. So we can get the total entropy generation. So delta S, the first one, if you want the numbers, the first one, negative 0.2258 joule, kilojoule per kilogram Kelvin, because it's been, actually this has been not kilogram, it's joule per Kelvin, kilojoule per Kelvin. This one, negative 1.2885 kilojoule per Kelvin. The surrounding was 1.925. This plus this plus this gives you the total entropy generation, which was 0.4017. It was 0.4107 kilojoule per Kelvin. Okay. So problem number 5, we have an inventor proposes an engine, heat engine. It means you can pay heat and get work between 25 Celsius and 10 Celsius. So you have T high and T low. He proposes that he's gonna have an engine between these two. T high was 27 Celsius. T low is 10 Celsius. Remember, we cannot these temperatures if we have ratio. For example, efficiencies. He said, I can produce 100 kilowatt. This is work net proposed. Can be correct, can be wrong. And I have just 20 kilogram per second in this cycle. And this is a seawater. He have 20 kilogram. So if you want to get the heat, this is part A and part B. If you want to get the heat for this problem, it's MC delta T. How much heat added here? You have the mass, flow rate. You have the C of the water, 4.2 kilojoule per kilogram Kelvin. You have delta T. Now we can use delta T, 17. It's okay. Delta T, Celsius and Kelvin, they are the same. So you can get the Q. Q high was, this is how much heat from this delta T. It was 1,428 kilowatt. That's good so far. So that's good. It's a little bit bigger than this. That's good so far. However, eta thermal has two definitions. So Q high, it's 1,400 kilowatt. So far it's good because it's bigger than kilowatt. However, eta thermal is two equations. Is one or W net over Q high, or 1 minus T low over T high. So let's get the maximum work he can get. So if we assume this equals this is the maximum work. So the maximum work, forget about his work now. The maximum work I can get is Q high, 1 minus T low over T high. That's the best thing you can do. Q high, we have it, 1,400 kilowatt. 1 minus T low, remember T low is in must be in Kelvin. It was Celsius. So you find that this is 80.86 or something kilowatt. This is the maximum I can get if I'm Carnot. This is if I'm a Carnot. That's impossible. He is lying. That's impossible to produce this work from this engine. The maximum I can get 80.86 kilowatt. If you propose 100, you are not giving the truth. Simple. For the last part, we have here derive the following equations. Beta H high, the COP for the heat pump. This is beta is COP. Heat pump is Q high over kilo over W net in. Guys, remember, do not use temperatures. And the other side, because this is general, temperature only if Carnot. Beta refrigerator is Q low over W net plus 1. If you take common denominator here, so it's W net over W net. So this is Q high over W net in, which is the same as this, required to prove. Part B, prove that beta refrigerator is 1 over eta thermal. Eta thermal is just this one. It's let's put it down. So this guy is output over input. Correct? And eta thermal is, this is -1. I can see -1. Minus, here is 1. So eta thermal is 1 over Q high, actually W net over Q high minus 1. It means the right hand side, it's Q high over W net minus 1, which means Q high minus W net over W net, which means Q low over W net. The same as this one, required to prove. So if you take the right hand side and simplify it, it would be the same as left hand side. That's correct. So we can prove or disprove a correlation between this performance. Just play with math. Common denominator, common simplify, it will be the same as the previous one. Just write it in terms of Q low, Q high, and W net. Do not use T low and T high unless it is ideal. It's Carnot. So for the last problem number 6, I give you the TS diagram. I ask you to plot constant TS diagram. Let's plot it bigger here. I brought for you constant temperature line, maybe saturated liquid, saturated vapor. I'll ask you to plot the pressure constant. The pressure constant, this is pressure 1 atmosphere. This is pressure 3 atmosphere, for example. 3 atmospheres, 1 atmosphere. This is temperature 100 Celsius. Be careful. I also give grade for accuracy. If this is 100 Celsius, constant temperature line, of course the 1 atmosphere should be overlapped according to table A454 saturated liquids. I wanted to plot S equals 7. So this is TS diagram. Yeah, TS diagram. This is TS diagram, so you need to plot S equals 7. So S equals 7 point, it will be here. Exactly betting this point, 7.6 something. So when you check the table, you find this is S equals 7 point. It was S equal 7.35. S.35 kilojoule per kilogram Kelvin. I want the volume 1.67. 1.67 also is here, passing through this point, something like this. This volume is 1.67 meter cube per kilogram. So be careful, you need to pass everything through this point. The larger, the smaller the volume, actually supposed to be upper. This is also, that's here. This is another one. Let's say V equal 0.5. I ask you for 0.5. So this is 0.5, this is 1.65. This is S equal 3.3. If I ask you for S lower, it will be left. S bigger, right. Of course, this is the x-axis is S. T, like temperature 100, 200, 300. The critical 357. Compressed liquid, subcooled, mixture, superheated. Saturated liquid line, saturated vapor line. Critical point. That's it. For last problem, part B. For last problem, part B, it's one of the problems in the homework. It's a house. Outside was cool, like, I don't know, T-low. I want the temperature inside to be 24 Celsius. I have a heat pump. It takes some power. It's 4 kilowatt. Yeah, this heat pump drop outside Q low and give me, take T low and give me Q high and give some power. So this plus this equal this. This is a heat pump in an engine. Determine the temperature. So I have T high. I don't have T low. I have the power. Yeah, I have heat capacity of the ceiling. This ceiling, I have C. So if you want to Q high, for example, it's MC delta T. Okay? So if this is per unit mass, just C delta T. So C delta T, you have heat capacity of this ceiling and you have delta T. Actually, you don't have delta T. You just have T high, but you don't have T low yet. So you have two unknowns. T high you have it, C you have it, and you don't know Q high yet. So we have this Q high function of T low. So let's say W net over Q high, I provided this way. So it's Q high, which is Q high minus Q low over Q high equal 1 minus Q low. It's look like the same energy, but it's not same energy. I just want to write this in terms of this. Why? Because this is ideal. It's 1 minus T low. Now it's better. Why? You don't know this, but you know that. You know this. And you know this, a function of T low. Ah, that means we have only one unknown here. So if you have this function of T low, and this is T low, everything here function of T low. So the only unknown is T low. Solve for T low. One unknown in one equation. You can start from COP, heat pump, or just simple like this. Both are correct. Both will give the same answer. The T low will be negative 0.567 Celsius. Again, you have heat pump in an engine, in a house. It has ceiling with semi heat capacity, so you can get Q high per unit mass. If you want to mark it per unit mass, like Q small like this, it's better. C delta T. You have C, you have T high, but you don't have T low. I don't know what is this. How much the temperature outside, I don't know. So that's, I don't know. Hold it. I have Q, W net over Q high. I have this. This, I have it function of T low. So this was Q high minus Q low over Q high, or 1 minus Q low over T high, or T low over T high. 1 minus T over T high, I have it. T low is unknown, and here T low is unknown. So you can write C delta T, which is T high minus T low. So you have this, you have this, you have this. You don't have T low. You don't have T low. It's one unknown between this and this. Solve it for T low. You can get anything. So this ideal pump, if it operates and take only 4 kilowatt, if it's ideal, if the temperature outside this, it can keep the temperature inside 24, as long as you give always 4 kilowatt. But if it's not ideal, if the temperature outside is almost 9 degrees like this, you need to give more power, maybe 6 kilowatt, maybe 7 kilowatt, because it's not ideal. So you get less efficiency. This is the maximum efficiency, and you are equal if you are ideal. Hope this helps you guys for your second midterm and solve all the homeworks, all quizzes, all lecture problems. Okay? Lecture 11, problem 2 and 3.